My name is Dione Janssen, and I will be explaining the topic of numerical methods. So this will be the general introduction to numerical methods. I'll be explaining a little bit of what it entails, and I will be talking about the errors. So first, I will be explaining three main topics of numerical methods in these coming videos. Namely, first one, topic of interpolation, and I will be focusing on polynomial interpolation, and the two methods that I will be discussing are Newton and Lagrange interpolation. Secondly, I'll be talking about numerical integration, and here I will be discussing the Newton Cotes formulas, and the first order one will be the trapezoidal rule. And then I'll also be talking about some higher order Newton-Cotes formulas, namely the Simpson's rules. And our third and final topic will be the problem of ordinary differential equations and how to solve them numerically. And I will be focusing on the initial value problems and how we're going to solve it using Euler's method, first of all. Then a slight improvement upon Euler's method, namely Hund's method, and finally the more general Runge-Kutta methods, and also the fourth order one, which will be the one that is most commonly used. So overall, this is a refresher lecture on the topic of numerical methods. I will be mostly focusing on the mathematical theory, so on what these methods mean mathematically, and I will be discussing some examples on how to implement this theory in order to solve problems. But like I said, it's only 2 hours, so this is going to mostly be focusing on the theory. And then hopefully in your masters you're going to be able to apply it yourself and write your programs using this. So I've used some resources for this lecture, namely these two books. First one, Numerical Methods for Engineers, and an Introduction to Numerical Methods and Analysis. The second one is goes a little bit more into the mathematical derivation and theory behind the methods as well, whereas the first one goes over a little bit more of examples for engineering problems. And then finally, I've also used this very useful website by the University of Alberta. The link is given here. And yeah, this website basically has all the theory that I will be discussing as well, a lot more elaborately, and also different topics of numerical methods. And they treat a lot of examples for engineering problems as well. They have codes in Mathematica, Python, MATLAB as well, and it includes lecture videos. So that one is very useful if you want to study a little bit more into the numerical methods at home for yourself. So here I'll briefly explain what numerical methods are. So numerical analysis is the study of algorithms for the problems of continuous mathematics. So obviously, since the widespread use and improvement of the computational power of digital computers, numerical methods have become increasingly more useful and more common to solve real-world problems. So numerical methods are sets of procedures to find the approximate solution to a problem. Yeah, so here a keyword is the approximate solution. You're going to try to get as close to the exact value as possible, but often you do not know this exact value. So a big part of numerical analysis will also be the error analysis. So how close is your approximated value to the actual value. So when I refer to errors in numerical methods, I will both be referring to the accuracy as well as the precision of a solution. So the accuracy refers to how closely a computed value, so your approximated value, relates to the exact solution. And precision refers to how closely individually computed approximations relate to each other or agree with each other. So you want to both maximize the accuracy and the precision to obtain the lowest error. And in this figure, just an example for a graphical depiction of what accuracy and precision means is presented. So this is just an analogy with trying to shoot at a target. And let's say that bullseye is your exact value that you are trying to approximate. And the bullet holes are your computed approximations. And then you can see in the figure A and C that the bullet holes are centered around a value that is not the bullseye. So that means that the accuracy is not very high, whereas figure B and D, the accuracy is high because they are centered around the correct exact value. And the precision is how closely the individual bullet holes are to each other. So figure C and D are precise, where A and B are less precise. So obviously you try to maximize both, and your lowest error will be in figure D. So we can classify errors as well. We have different types of errors. So first of all, we have a round-off error, which is the difference between a rounding approximation of a number and its exact value. So for example, instead of using pi with an infinite amount of decimals, you're going to use 3.14. So then your error is going to be 0.0015, etc., etc. Usually computers store a lot of decimals, but if you have a computer program with lots of steps, you might find a significant rounding error if you round the values in between the steps. And secondly, we also have a truncation error, and this is an error that is caused by approximating exact mathematical procedures. So this error is usually inherent to a certain method that we're going to use, and this one you can estimate. So for example, if we have the exponential series, you have this infinite sum, 1 plus x squared over 2 plus etc., etc. And obviously you cannot use an infinite sum, so let's say we will use only the first two terms to approximate this exponential series. So this means that your error is going to be the third term and higher. So we can define errors also in different ways. The simplest way of the absolute error, which is just going to be the difference between the true value and your approximation. So E is Vt, true value, minus Va, your approximated value. But this, however, does not take the magnitude of the values under consideration into account. And so if we want to account for this, which you might want to normalize the error to the true value to obtain the relative error. So here ER is E over Vt, so for the true value. So in most situations where you want to apply numerical methods, the true value is actually not going to be known. And therefore, you will use an approximation of this error. So you get relative error is the approximation of the error over the approximated value. And often this approximation of the error we can approximate depending on which method we're going to use. And I will be discussing what the truncation error is for a lot of these methods as well. So another useful notation in the error analysis is the big O notation. I'll be using this in the videos as well. So it is more formally known as the asymptotic order notation. So let's say we have a true value, again, Vt, and an approximate value, Va, that depends on the parameter h. And usually we'll use h for the step size. So if h becomes small enough, so if we have small enough step size, then we can say that this true value is approximately equal to our approximate value. That's obviously what we want. Now, if we can find a constant c such that this difference between the true value and the absolute value, so the error, is smaller or equal to c times some function of h for all h when h is sufficiently small, then we can say that this difference, Vt minus Va, is equal to big O of this function of h. And this allows us to concentrate on the important issue of the dependence of the error on the parameter h, and it allows us to ignore less important details such as the exact value of this constant c. So we can kind of see how the error changes if you change the step size. An example for which the big O notation might be used is again for infinite series. So here we'll have the exponential series again, and instead of using infinite sums, we can approximate it, for example, using the first 3 terms, and then the error is going to depend on x to the third. So we'll have big O of x to the third. And note that this is equal to the expression below that. If we use the first 2 terms, your error term is going to depend on O of x to the power 2. So these 2 expressions, or these 3 expressions, really are equal to each other.